Okay, so this is 8.3 and this is rational functions. Okay, so let's start with direct proportionality. What's direct proportionality? Let's think that we want to build a pool, a swimming pool. Okay, we are looking at it from above. And this swimming pool has, like, let's say I have space for a 4 meter wide swimming pool and the length is variable. Okay, I don't have a fixed length, I can change it. And then my volume for the pool, sorry, my area for the pool is 4x, okay, because it's width times length. So the area is 4 times x. The area is going to be y. Okay, this is direct proportionality. The longer my pool is, the more area I have, the more surface I'm using for my pool. That's direct proportionality. As this length grows, my area for the pool grows. But what happens if I change things here a little bit? Let's say that my pool has a surface of 30 square meters, okay, and it's fixed. But I'm going to use two variables to determine the width and the length, okay? So my pool is x times y equals 30, okay? That's the area of my pool. What happens here? Here, this is no longer direct proportionality. This is inverse proportionality. Why? Because if I isolate y, this is 30 over x, okay? And this is a rational, well, if I write f of x here, this is a very simple rational function, but it's a rational function. And this looks like this. Like if I graph this, it would look like this. Okay, and here I'm going to share my screen and I'm going to use GeoGebra here because it's way more visual, like it's easier to see that with a more accurate tool. Okay, so I'm going to present my whole screen now. Okay, and I'm going to plot that equation, that function. And this is 30 divided by x. Good. And this is what it looks like. Okay, so my pool, as we said, has a width of x and a length of y. So if my width is 30 meters, my length is 1 meter. Okay, because 30 times 1 is 30. If my pool is 15 meters wide, it's 2 meters length, 2 meters long, okay? Then if this is 6, this is 5, okay? If it's 5 here, it's 6 here, okay? And it's the same on the other side. So if this is 2, this is going to be 15. If this is 1, this is going to be 30. Okay? You see that that's the inverse proportion, okay? If the pool, like the x is very small, if it's very narrow, it's going to be very long. If it becomes wider, it becomes shorter, okay? At this point, the pool will be a square. And then here, it changes in the other side. It's very wide, but it's very short, okay? And there's something I want you to realize here. You know that my pool, like, let me go to the board for this again. My pool, okay, so this is a normal shape for my pool. If I can make it narrower, okay, and it will be longer, okay, because my area is fixed. I could Okay, or let's do it, yeah, like this. If I make it very narrow, it will be longer. Okay, let's visualize that I make it very, very, very narrow. Okay, so it will be very long. Let's think of something which is nonsense, like it's, I don't know, kilometers long. So this x is very, very, very small. Okay, we will be going to values up here, like as an x very, very small. So y is super, super high. Okay, but even though my pool is kilometers long, it will always have a width, okay? Even though it's millimeters, but it will always have a width. Even though it's 0.01 millimeters, it will never be zero. The width or the length, it cannot be zero, because if it's zero, there's no pool anymore, okay? So even though it's very, very small, there will always be some length and some width, right? That's an asymptote. It's a value that I approach, but I never touch. Okay? Here, this y or this x, they can never be zero. They will be very, very close, but it will never be zero. And that's, again, that's easier to see in GeoGebra. So I'm sharing my screen again. Okay, so let's see that here. If x is very, very small, you see that this goes up and up and up and up, and it seems like it's touching the axis. It seems it's over the axis, but it's not. If I get closer, I see there's a distance here. I could go up and up and up and up and more, okay? And at some point, it starts to seem again that we are over the axis, but if we get close enough, it is not, okay? This is an asymptote. We are never, ever touching the axis, okay? So there is a line here that we usually represent as a dot line. We can make it in red. And that's an asymptote. It's a line we approach, but we never touch. Okay, that's why the domain is so important in rational functions, because they have vertical asymptotes all the time. Sometimes they do have horizontal asymptotes as well, not always, but they always have vertical asymptotes. Okay, so those are very characteristic of rational functions, and that's why they are very important and they define the domain. Okay, so I'm going to stop recording here.